started with the product topology then? Yeah. So before we start with that, we have to define what the general product space is, which we skipped out from chapter 5. Yeah, section 5. Yeah. Okay, so a J tuple is essentially, so we have an index at J, so that must exist from somewhere. And then we have, a function that goes from J to, a collection, right? And yeah, that's about it. This function is it. Yeah, so sorry, it's a set. It's a collection. A set doesn't really matter much, but yeah. So a function from J to a set is called a tuple, and the value at each point of the index set is called the coordinate, I believe. Yeah. Okay. And okay, so if we have an index set A alpha, is it J or alpha? Yeah, it's J. Okay. So we define the product of these the product, so what, the space or what? Cartesian product, yeah. We call the Cartesian product as what? X, the set of all such functions. So, yeah. And we take their union. So that's going to be equal to X. So we take the set of all such functions such that X alpha belongs to A alpha, right? Yeah, you take their union and you get a set. You take the set of all functions such that each coordinate lies in the index of the index, the set at every index, the same index with, so yeah, we have a condition too, right? Yeah. And oh yeah, X alpha is essentially X of alpha, same thing, right? Yeah, you take all the functions and then that's how you define the Cartesian product. So yeah. Okay, yeah. Now we can define the box topology. So similar to the, pi of X alpha, so we can have X alpha as a bunch of spaces. We can have pi of U alpha. Essentially, we just take the set of all functions that the coordinate lies in one of the UI, right? So at every stage. Yeah. Okay. So this is the basis for what we call the box topology because, we just have to check that it's basis, right? Then we'll be done. So for that, we have pi U alpha intersection pi of V alpha is equal to pi of U alpha intersection V alpha. And why is that? That's because you take a function that lies in both of them, then it's going to its coordinate will be lying in both of them essentially. So at all coordinates, it's going to lie in, and that's all we need to really check. And this is an open set by definition. So yeah, yep, okay. So it's the basis, and the topology generates is defined to be the box. We can define the topology from a basis. Yeah. Okay. Now, we observe that in the regular X cross Y Cartesian product, which is also definable in this way, this thing, what is it? Yeah, pi inverse 5. So the first coordinates inverse of the inverse image from the open set, right? Union the set of all such things, union the set of all by two inverses. This formed a subbasis for this, right? And the topology generated by the subbasis was the same thing here, right? So similarly, we can define the product topology from the general inverse images from the projection functions. So yeah. So U alpha is an open set. Pi inverse of alpha is the inverse image from the projection function, and you take the union across all alpha in J, and that is a subbasis. So it's a subbasis because you just take, well, pi inverse of alpha, U alpha, and then pi inverse of beta, U beta. Beta is not equal to alpha. To take the union, what's going to happen? So the inverse image is going to be the whole space in all but the alpha coordinate, right? And this will be the whole space in all but the beta coordinate. And you take the union, you'll get the whole space. across all coordinates. So yeah, the union is the whole space, and that's why it's a subbasis. And from that, we can get topology. And the topology from the subbasis will not be the box topology, and or they will be if the Cartesian products are finite. So yeah, that's what we prove now. So yeah, by definition, a basis element generated from the subbasis is all the finite intersections, right? So if we make the finite intersections, we can have a, a proper open set. So not the whole space, whole set or the empty set, a proper whole set, open set, essentially multiplied finitely many times, right? So because we can get a finite multiplication like that from a finite intersection, we can uh, we can have the product and the box topology be equal if the Cartesian product is from a finite intersection, index set. So what now? Now, yeah, now we just have to show that the box topology is finer than the product topology, and then we can have every comparison there is. Because the product topology certainly isn't finer than the box topology if the index set is infinite. And we'll discuss an example later. Yeah. Yeah. Okay. Yeah, and that's how you get the definition of the basis elements of the product topology. So it's just the finite intersection of the inverse images. Okay. Now, yeah. So, okay, so the product topology is coarser than the box topology because any open set is going to have be the, so any basis element is going to be the finite intersection, right, of inverse images, right? And this is going to turn out to be phi of u beta. I'm going to call it alpha, I guess. Where if alpha is beta I, then it's going to be u beta I. But if it's not equal to any of these, then it's going to be the whole space. And the whole space is an open set, and these are open sets, and therefore it's in the box model. Now, in the other way, yeah, you take a proper. So if you take the infinite set, you take the infinite set of natural numbers, right? And you have a proper open set in all of them, right? So if you want to take the standard topology, then let's just take a minus one to one. So that's not the whole space, and not and also an open set, and it's not empty. But empty is not really relevant here. So you take this multiplied with itself infinite times. So this is what the product topology, but on the index set being the set of integers, positive integers. Yeah. So you cannot achieve this set from the sub basis of the product topology. You can only achieve it to the box topology by since they're all open sets. So it's strictly finite is what I have just proved. Yeah. Okay. Yeah. I think I'll prove theorem 19.2 till 19.5 here itself rather than the exercises. So let's go with that. Yeah. Okay. So since the topology is it's given by the base. Okay. So we have a basis for each topology, right? And yeah. So now we have a collection of all the sets of the form B alpha, where B alpha is belonging to B collection alpha, right? Yeah, so the collection of all these products is supposed to form a basis for this product, right? So first of all, these are a collection of open sets because the basis is always a collection of open sets. So every element here is also a basis for the topology here. It's a basis element, right? If we follow the definition, so it's a collection of open sets, right? Because that's what it means to be a part of the basis. So now we just have to check that if we, yeah, so if we show that every basis element here is contained, contains an open set here. Wait a second. Yeah, so if we show that every open set here is contained by this basis, yeah, so if we show that this makes a basis limiter, right? So we're going from this basis to this basis. So they both are supposed to be a basis for the same topology, right? So we take any open set here, it's going to have this some element here as a basis, and we just have to show that some element here is, so for every x in here, so I'll just write that element here. I'm just going to write it as pi u alpha. So yeah, so we have this arbitrary basis for the arbitrary open set, and now we just need for all x in here, there exists a basis element. Yeah, basis element. So I'm essentially using theorem 13.3, but with both of these as a basis. And one containment is trivial because it's containing every member. The other containment requires the, yeah, such that x belongs to this and this is a subset here, right? So how do we show it? Yeah, so we use the fact that B alpha is the basis for x alpha, right? So because of that, for every x alpha, so this is a coordinate actually. This is a function, right? We have a coordinate for this. So every x alpha will belong to B alpha and be contained in U alpha. That's the definition of the basis and our assumption. Now, now what? Now, yeah, so you take the product x, since x alpha is belonging to B alpha for all of them, the entire function must also belong to the product B alpha. And it's a subset because, well, B alpha is a subset and U alpha is a subset, and essentially the product the subsets carry over for products, and that you can check from the definition. So any function that lies in B alpha, and B alpha is in U alpha, it's contained in U alpha, then that function's coordinate will be there. And it's going to be true for every coordinate. So yeah, you just apply the definition of the Cartesian product, and then you'll get that the containments transfer over. So I'll just write it down for all B alpha, U alpha, V alpha is contained in U alpha implies product, it belongs to J. So I'm just leaving it out as an exercise essentially because I've orally proved it, right? So the definition, you have to use the product definition to use it to write the proof problem. Yeah. Okay, so that's all theorem 19.2. Now theorem 19.3. Yeah. Let's see. Let A alpha be a subspace for each that. Okay. Okay, so if both the products are given in the box or the product topology, then the subspace topology happens. So yeah, yeah. So where were we? Yeah. So I'm going to call the subspace topology as A and the product topology as A alpha. So we're taking the subspace and then multiplying it. That's A alpha, right? Yeah. So you have to show that these two are the exact same essentially, right? So rather than going, the subset route, I'm going to just show that they're both defined in the same way, right? Yeah. So how are these defined, right? These are defined as, so pi A alpha intersection open set, right? So these are open sets in the product topology or box, doesn't matter. And these are defined as what? Let's see. Yeah, pi of A alpha union U alpha. Okay, it's not that though. Wait, this is subspace? Yeah, this is actually, okay, yeah, this is exactly that. Yeah. And the reason these are the same is because for every open set, there exists a basis element. So for every member of the open set, there exists a basis element that contains this essentially. So for every x, there exists, you know, there exists a basis element that's contained here, right? And yeah, once we've gotten an open set, we can just union it and then get this thing. So we can achieve any element here from the union of these elements, right? And of course, all elements here are contained here. So because these are all actually open sets, right? So yeah, and that's how we show that there's the same topology. So it comes down to the definition essentially. And yeah, if you understand the definition, writing a formal proof is a bit harder because you have to write everything properly, but understanding why it's true is a different thing, and that's a lot easier. So yeah. Okay, if yeah, Hausdorff, right? So if each x alpha is Hausdorff, then yeah, okay. So take let's take x and y that are not equal, right? If they're not equal, then they must at least differ at one point. They could differ at exactly one point, but at least one point. So let's call that x alpha, right? Yeah. Okay. Now what? Now, yeah. So this space is actually Hausdorff, right? So now what? Now there exists u alpha completely disjoint from u alpha, v alpha, right? Or I'm going to call them ux, I guess. Yeah. So we have a ux and uy that are both open sets and disjoint by Hausdorff, right? Okay. Now note that if their intersection is empty, then even if you take the entire open space, right? So let's say you take essentially, I'm going to call it y alpha, I guess, such that y alpha is x alpha if beta. Y beta is x alpha, x beta if alpha is not beta, and otherwise it's ux and ui. So we have y beta x and y beta y. So what are these? These two are open sets in the product topology, right? Since we're taking the whole space, and their intersection is pi at one coordinate, and therefore, due to the rules of Cartesian products, there is no function that can actually have a coordinate value at one of the coordinates, and therefore there is no function, and therefore these are also disjoint. So if every space is Hausdorff, then the product is also Hausdorff. Okay. Now, and yeah, note that we use the product topology here to prove because the box topology automatically will have one. So we just need the existence of something, some open set, right? In the so even if it's in the box, a product topology, then it's also there in the box topology. So yeah. Okay, should I do the closure one? Hmm, yeah, fine. Okay, so pi of a alpha closure is equal to pi a alpha whole closure, right? Okay, so yeah, to show that a limit point belongs in the other category, we'll have to use the x belongs to a limit point a closure theorem, right? In fact, we could go with the whole x does not belong to a closure route as well because they're both subspaces, yeah, subsets of a space. So if you want, we can also use the not implies not and go both ways, right? Yeah. Okay, I have to do something else. Yeah. Yeah. So let's prove 19.5 using this method essentially. So, not implies not. So that also works out, right? Yeah. So let's say x does not belong to 1. Yeah, x does not belong to 1, right? Yeah. So that means there's a neighborhood in how, like, right? That matters. Okay. So, hmm. So, okay, x does not belong to 1, and the set here in question is okay. So the closures matter here, right? So the sets, yeah, we're closuring them in different ways. Okay. Okay, if x doesn't belong to 1, then that means there exists a neighborhood for each coordinate essentially, right? That's the only way it can. So yeah, if there exists a single neighbor, if there does not exist a neighborhood for some coordinate that's such that their intersection is disjoint and this contains x, then x will end up belonging to this closure, right? So let's proceed that way. Yeah. So there exists u alpha such that u alpha intersection a alpha is phi and x belongs to u alpha. Is that good enough? Yeah. So I'm intentionally changing the proof as an exercise. So that's how this works. Yeah. So x is yeah, this such a u alpha exists at every coordinate. Now we have to show that x is so x is a vector here. So a vector is also a tuple, same thing. I'm just naming it here. Yeah, x is supposed to belong here, right? So do we have a product in the big topology, right? That's the question. Yeah. So here, this means that x does not belong to a alpha closure for all alpha, right? Yeah. So now we need to have that x doesn't, yeah. So can we generate an open set in the big topology, right? In the product or box. So yeah, let's try product. Then that would enable us to give a more general statement. So we need an open set in the product topology that such that it's not intersecting this vector. How would we do that? Actually, yeah, we don't even need to do much. We just need to be different at some coordinate. So yeah, let's say phi inverse of u alpha, right? That's an open set, right? Okay. Now x is going to lie here. The entire vector is lying here, right? And by assumption, this is phi. So this phi inverse in u alpha intersection, how do we write it? Yeah, phi of a alpha is phi because at one point their intersection is phi. So yeah, we found one in the product topology and therefore also in the box topology. So not one implies not two is done for the product topology, right? And therefore the box topology. I suspect the other one does not require this generality. I'm not sure. So one of them is going to be easier. Okay, so not two implies not one. Let's try that. So x does not belong to here. That means there exists a u that's open. So we don't know how open it is, but we do know that there's a basis element. And if there's a basis element in the product topology, then we're done. So let's try that. Hmm. Okay, so if it's in the basis element of the box topology, we'll have to do something. Yeah, let's just do it. U open in phi x such that u intersection. So yeah, now we're not using each coordinate. Now, so one can be a bit easier actually. So note that we're introducing the entire product now. Yeah. So Yeah, I think it comes down to the fact that this being phi, if and only if at one coordinate the intersection is phi. So that's what the equivalence comes down to. And you can see that more clearly with this proof. I think it's there. Yeah. So how do we approach this? Let's see. Okay, so this U contains a basis element in the product and the box topology. So let's work with that. Mm, yeah, okay, so even if it's in the box topology, we can, yeah, from that box topology open set, we can get the product topology open set from just checking any one. So this can happen only if there exists an alpha belonging to J such that U alpha intersection A alpha is phi, or at least this direction is trivial. Actually, yeah, the other one too. So they are equivalent. Yeah, this is actually the core of it. I didn't even have to go that much further. This is it. This is the entire proof. This is both of them. So yeah. And at one, so this, and yeah, you have to prove it for the open set in the box topology, which is quite trivial, and the product topology as well, because you'll have to choose that one carefully. So there exists an alpha. That's true, right? Suppose there doesn't exist a single one, then well, how are we getting the empty set in the product topology? In the box topology, you just hang on, is it more less trivial in the box one? No, in the box topology, you have the basis element, so you're fine. Yeah. So yeah, there is absolutely no problem here, and this is the root of the proof. Is root the right word? Probably not. Crux, I guess. I'm not sure. Okay, now the continuous if and only if thing. Yeah. So f is a function from a to the product. Yeah. And f alpha is equal to pi alpha composed on f, right? And f is continuous if and only if for all alpha, f alpha is continuous for the product topology. For the box topology, it's this direction. So how do we show that? So I'll just show this one for the box topology and yeah, okay. Yeah, so let's see. So note that pi alpha is a continuous map and it's an open map and yeah, those two are it. So it's an open and continuous map. I think I showed it already. And f is a continuous function, so f alpha is going to be continuous. So one direction is trivial. Yeah, so this direction is always trivial. For this direction, yeah, that's where the product comes in. So pi inverse alpha is by definition an open set, right? It's the subbasis. And that's what we're going to take advantage of. Yeah. So so you need an open set here. So if we show that a subbasis being sent backwards is fine, then we're done. So yeah, we take the subbasis, right? And we take its, yeah, we're done this way. Yeah. So F alpha composed on that is, hang on, something's wrong. Oh yeah, okay. F alpha inverse is equal to F inverse uh, of pi inverse, right? So they flip around, right? That should be fine. Yeah, I think I proved it in section 2. Yeah. So from that, U alpha is in, yeah. Oh, wait, sorry. Hmm, I'll have to check a bit. Okay, so we're using the fact that if the inverse image of subbasis element happens to be open, then this function, so this is the subbasis element, this is the function, and if this entire thing happens to be open, since this is open by definition, then the entire thing is open, right? But note that because of this relation, this is precisely equal to F inverse alpha, U alpha, right? So you take, so since this choice was arbitrary, the choice of alpha here, we need every F alpha to be continuous, but since every F alpha is continuous, we can use the equality and show that this the inverse image of an open set is an open is a sub of a subbasis is an open set. So yeah, that's how we show that F is continuous. So yeah, is anything left? No, that's an example. So I'm not getting into that. Yeah. Okay, let's do the exercises now.